Hello class, this is day 23 of Coronachem. Now this is period 4 for grade 12, and the question I gave you for homework yesterday was a doozy. It was as follows. A 35 milliliter sample of 0.15 molar acetic acid is titrated with 0.15 molar sodium hydroxide solution. Calculate the pH after the following volumes of base have been added. 0, 17.5, 34.5, 35, 35.5, and 50 ml of base. So what I did to solve this problem was to create a data table just to compile all the data into one spot, and then I'll show you what the data table looks like, and then I'll start solving problems one at a time. I don't know how far I'll get into this problem. This problem is so long that it might be even too much for one question on a test, but we'll see how the timeline goes. So we have a 35.0 milliliter sample of 0.15 molar acetic acid, CH3COOH. And let acetic acid be symbolized by HAC. It's just going to make it easier to do the calculation. And then, so that would be CH3COOH. And then the acetate anion we can symbolize by AC with a minus charge on it. And that is representing this thing. The table looks like this. I have a 1, 2, 3, 4, 5, 6, 7 headings. So it's going to be NaOH added, moles of NaOH, total volume, because remember, the concentration of substances changes if you add more solvent. And whenever you do a titration, you're necessarily adding one thing to another. So the total volume is the sum of the two substances that are being added together. So I'll do it in milliliters and liters. So I'll indicate which substance is in excess. And the ratio of acetate anion over acetic acid, the ratio that you get. And finally, the pH that results. So this is the answer for A. Actually, I'll show you what I wrote, and then I'll show you how I solved each one, because that way you'll have at least a compilation of all the answers that I got, and then you can compare your own with it. I know I showed you yesterday, but I don't know how much of it you saw, so I'm just covering all the bases. So the amounts of titrant added were 0, 17.5, obviously this is in units of milliliters, and 0.15 molar sodium hydroxide. We have 34.5, 35. Oh, there's an F. It's going to be tricky. 35, 35.5, and 50. So how do I get the moles of NaOH? I'm going to use the equation N is equal to mV. So I'm going to use N equals mV. And for example, if the molarity is 0.15 and we have 35 1/1000ths of a liter of titrant added, what we get is 5.25 times 10 to the negative 3 moles. So I'm going to write these values here. So I'm doing this calculation to get this value. I'm just going to put a little star here so you know what I'm doing. So there's 0 here, obviously. Here we get 2.625 times 10 to the negative 3. In fact, they're all times 10 to the negative 3, so instead of writing times 10 to the negative 3 6 times or 5 times, I'll just write the first part of the scientific notation. So all of these numbers are times 10 to the minus 3. So just keep note of that. 5.175, 5.25, 5.325, and 7.5. The total volume of the solution is 35, 52.5, 69.5, and you'll see that by doing calculations like this, especially when you do lab reports and things like that, you don't want to be doing the same calculation 7 times. Well, you're going to do it 7 times, but you can do it in your calculator, and then you can compile the results on a data table. This is a much better way of putting together data. And then very often when you're drawing a graph, you're also going to need a data table. So 70, 70.5, and 85, which if you convert to liters, I'll just have, that's a subset here, 0.035, 0.0525, 0.0695, 0.070, 0.0705, and 0.085. Then, which substance is in excess? In this case, it's the acetic acid. And the same with the next two. D is the equivalence point, so there is no excess. They're exactly equal amounts have been put into solution. And in the second half, sodium hydroxide is what is in excess. So in this case, there is no ratio. I put a star in there, and I didn't explain what the star is. It may be referring to, okay, it refers to a calculation. That's part D. So, okay, so the ratios here are 2.625 times 10 to the negative 3 over 2.625 times 10 to the negative 3. That's the halfway point. Here it's 5.175 times 10 to the negative 3, and here it's 7.5. Times 10 to the negative. It says 5. I think it might be 3. Now I'm not sure. This I do a calculation later, and here it's not applicable because you're in excess. So you can't use the Henderson-Hasselbalch. These two we're doing because you can use the Henderson-Hasselbalch equation to solve for. If you're at the equivalence point, you don't use the Henderson-Hasselbalch, you use the counter ion, the acetate anion concentration, and then it's going to give you a slightly basic solution. So we're going to do that calculation separately as well. So the ratio here is not applicable, and neither is it here. And here the ratio is 1 to 1. Here it's 1 to 69, or 69 over 1. Okay, this must have been a minus 5 then. That's what it was, because the ratio is 69 to 1. Right, and the pHs I get for each one of these are 3.52. So if you got all the right answers, you don't need to listen to my explanation. It means you understand. If any of these answers don't match your answers, then you need to listen and find out what you did wrong. Okay, so there we go. 12.42 is the last one. So just quickly calculate those, and then I'll show you how to do part A. We get A, B, and then all of a sudden it jumps to all right. Okay. C, D, E. Okay, so I'll erase now. Hopefully you've had enough time to copy. First one is before you even start titrating, you're asked to find the pH. And it's essentially a solution of acid with a concentration of 5.25 times 10 to the minus 3 moles of acid no, it's a 0.15 molar concentration of the acid. Guess what? I did the wrong thing on A. For A, anyway, so the answer for A is wrong. I'm going to fix it in a minute. So 1741A, 0.15 molar acetic acid, no titrant added. So acetic acid does this. CH3COOH is acetic acid. It's a weak acid. It dissociates to give you the acetate anion and the proton. If you're starting off with a 0.15 molar concentration, this is a very easy calculation for you by now, hopefully, if you've been following. Starts off with 0.15 molar concentration, a certain amount of it dissociates, call that X, and the equilibrium we get 0.15 minus X. The acetate anion concentration starts off at 0, a certain amount X dissociates, and at equilibrium X is sitting in solution. Same thing happens with the proton. The Ka of acetic acid is known to be 1.8 times 10 to the negative 5. So this equation turns into the equilibrium concentration, the equilibrium constant equation, which is acetate anion concentration times proton concentration over concentration of the undissociated acid. And that's represented by x squared over 0.15 minus x. Allora, 1.8 times 10 to the minus 5 times 0.15 minus x equals x. You might be able to use the approximation in this case, but I don't like using the approximation. I'm just going to use the actual numbers. So 1.8 exponent negative 5 times 0.15 gives you 2.7 times 10 to the negative 6 minus 1.8 times 10 to the negative 5x equals x squared. So it generates a trinomial x squared plus 1.8 times 10 to the negative 5x. Chiudo la porta, sennò crea disturbo. So I've transposed that over to this side. Minus 2.7 times 10 to the minus 6. All that equals 0. So we're going to put that into our calculator to calculate the equilibrium concentration. This is an equation, quadratic. First number is 1, the number that appears in front of x. The coefficient for x is 1.8 exponent negative 5. And the number is negative 2.7 exponent negative 6. And you get two values for x. 1.634 1 times 10 to the negative 3 and negative 1.651 times 10 to the negative 3. This is the one you keep, this one you discard. This is going to equal the H plus concentration. So pH, which is equal to the negative log of the H plus concentration, is equal to enter the whole number. And there's one little thing about this calculator. You got to go switch modes so you can't keep the number. That or I don't know what I'm doing. 1.6341 9232 exponent negative 5, and the pH, whoops a daisy, the log of that equals what? 4.7866 0.96. So we're going to report pH always never past 2 decimal points. So what we write is 4.79 as your answer for part A. Did I get that right? No, I put 3.52. I copied the wrong number. Sorry about that. So my 1741A is wrong. And you could have had a bonus, but you didn't do your homework, so too bad. B. 17.5 milliliters added. Now, because we're adding a titrant, some of the acetic acid is going to be titrated, and you're going to get acetate anion. So when you have a mixture of a weak acid and its conjugate base, you have a buffer. So let's see, when you have a buffer, you're allowed to use the Henderson-Hasselbalch equation to calculate the pH. So let's do that. Henderson-Hasselbalch equation is as such: pH is equal to the pKa plus log of the conjugate base concentration over the acid concentration. In this case, after the addition of 17.5 milliliters, you know what I just realized? I realized I did a whole bunch of stuff wrong here. But it works out anyway because the amounts are the same within the same solution. So as it turns out, you get the same result. All right, so concentration of acetic acid, concentration of acetate. So after addition of 17.5 milliliters, you've added 2.625 times 10 to the negative 3 moles of NaOH to 5.25 times 10 to the negative 3 moles of acetic acid. So we're going to subtract, we're going to have this much AC. You're going to have this much times 10 to the negative 3 moles of acetate anion, and you're going to have this minus this of acetic acid. So let's just double check that one. So 5.25 exponent negative 3 minus 2.625 exponent negative 3 of that one, and what you get is the same number because it's halfway. 2.625 times 10 to the negative 3. So the ratio of moles is this to this, and they're both in a total volume of, what's the total volume? 52.5 milliliters. Or 0.0525 liter. Now I could find the concentration of these two things, but guess what? It doesn't matter because they're the same amount. They're going to have the same concentration. So there's no point doing the concentration calculation on that. You're going to get a ratio of 1. So in this case, the pH is going to equal the pKa. Remember how I told you that when you have half of your weak acid ionized, the pH equals the pKa? Here's the case of that exact thing. So the pH equals the pKa of, well, let's find the pKa because I only remember the Ka of acetic acid. It's 1.8 times 10 to the negative 5. So pKa is equal to the negative log of Ka, which equals log of 1.8 times 10 to the negative 5, or, was it 4.74? Yeah, you get 4.74. So pH equals pKa plus log of these two numbers, basically this number over that number, but it gives you the log of 1, which is what? It's 0. So pH equals pKa plus 0, so therefore it equals 4.74. Okay, I guess I got that one right. Yeah. The next step is after the addition of 34.5 milliliters. So just take a look at that. Maybe stop the video if you want. That way you can copy it. On part C of this titration, we've added 34.5 milliliters of the titrant, of the base. And it creates a ratio. I'll show you how I got the number. So you have how many moles of base? 5.175 times 10 to the negative 3. Or 5.175 times 10 to the negative 3. How did I find that out? I used N is equal to molarity times volume. The molarity of the base is 0.515 moles per liter. You added 34.5 thousandths of a liter. So that gives you 5.175 times 10 to the negative 3 moles NaOH. So the concentrations of the acid and the acetate anion. The acetate anion concentration is going to be essentially that, because you've added that much NaOH, so it pulls off that many protons. So you're going to have 5.175 times 10 to the negative 3 moles of acetate ion in solution, and your acetic acid concentration is going to be 5.25 times 10 to the negative 3 minus 5.175 times 10 to the negative 3. So that gives you a very small amount. 5.25 minus 5.175 gives you 7.5 times 10 to, oh my goodness, what am I doing? Let's try that again. 5.25 exponent negative 3 minus 5.175 exponent negative 3, and you get that, 7.5. 7.5 times 10 to the negative 5. Please don't tell me I got that wrong too. They're both in the same solution, of course, so really the only thing that matters is how much of each is present. So the ratio of this to this is what we're caring about. So we're going to say that number divided 5.175 exponent negative 3, it gives you 1/69. So basically the pH is equal to the pKa plus the log of A minus concentration over acid concentration. pKa is 4. What is it again? 74? Yeah, 4.74 plus log of 69. No, so log of, 69 over 1. This one is higher than that one. 69 over 1. And you're going to get log 69 equals that, 1.83 plus 4.74. And you get a pH of 6.5788. So when you report it, you're going to say 6.58. That's the pH just before the equivalence point. Okay, did I get that one right? Yes. All right. Now we're going to find the pH at the equivalence point. So we add exactly 35 milliliters of the 0.15 molar sodium hydroxide. So you're going to have added the same number of moles of sodium hydroxide as there are moles of acetic acid. So that's going to bring the reaction to completion. But now what's going to happen is the only thing you have in solution is the sodium acetate, the counterion, the conjugate base of acetic acid. So now the pH is given by the acetate anion. My brother was looking at me through the window. So the pH is going to be caused by the acetate anion pulling a proton off water to give, to reconstitute base. So now the challenge is to calculate what the value of Kb for the acetate anion is. and then calculate the concentration of the acetate anion, and from there establish the equilibrium, and then calculate the pH. So here's what happens. You have acetic acid, so this is D of 1741. The acetic acid dissociates, reacts with base, no, doesn't dissociate, it reacts with base. And you get sodium acetate still in an aqueous solution, basically. So the ions are sort of floating around in the solution, but they're completely soluble, and then you get water. And then at equivalence, when this reaction goes to completion, all you have is sodium acetate and water, because the sodium hydroxide reacts fully with the acetic acid. So now what happens is the acetate anion floating around solution can pull a proton off the water and reconstitute the acetic acid, and it'll generate hydroxide in solution. Now we need to find out what Kb is for the acetate anion. Remember that Kb for the conjugate base is given by Kw over Ka of the acid. Kw, you know, Kw is 10 to the negative 14. Ka for acetic acid is 1.8 times 10 to the negative 5. So what you get for the value of Kb is 5.5 recurring times 10 to the negative 10. So now we can establish the equilibrium, which is concentration of acetic acid times concentration of the hydroxide ion over the concentration of the acetate anion. And that's going to be represented, just, you could use an ice table. I can go through a whole rigmarole of drawing you an ice table, but bottom line, what you get is this: x squared over 7.5 times 10 to the negative 2 minus x. How did I get the concentration of the base? It's going to be 5.25 times 10 to the negative 3. But now the total volume, let's just double check the answers, because I actually don't trust myself on this. 5.25 exponent negative 3 divided a total volume of 70 at equivalence. So 5.25 exponent negative 3 divided 0.07 gives you 3/40, or 7.5 times 10 to the minus 2, which is what I had written here. And all this equals 5.5 times 10 to the negative 10. Okay, so that's going to generate a trinomial. Let's see if I have it here. Yeah, the trinomial you get when you redistribute this equation is x squared plus 5.5 times 10 to the negative 10x minus 4.16 times 10 to the negative 11, and all that equals to 0. When you put that in your calculator, you're going to get two answers, or if you use the quadratic formula, you're going to get 6.454, 694, 471 times 10 to the negative 6, and that equals your concentration of hydroxide ion. The other number that you get is negative 6.45, blah, 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 times 10 to the negative 6. You reject that value anyway. So the pOH is going to equal to negative log of the OH minus concentration, which in this case ends up being 5.19. So the pH is equal to 14 minus that number. And what you get as a final answer is 8.809, 8756, or you would write 8.81 as your final answer for the pH of a solution in which acetic acid has been titrated. Now, for the last part, E and F, the pH is overwhelmingly attributable to the presence of excess base. Once you get over, once you pass a pH, like remember, every time you go from pH one value higher, you're getting 10 times the concentration of hydroxide. So from pH 8 to 9, there's 10 times as many hydroxides as there are. in the lower pH. And when you go from 9 to 10, it's again 10 times more. So now we're already going into pH 11 and pH 12. So now the weak base and the conjugate base has no effect on the pH. You're looking at the effects of a strong base. And that's a very simple calculation. You're just finding out what the excess concentration of base is. I'll do a D and E for you because they're pretty, E and F for you because they're pretty short calculations. What did I do here? I actually included the effect of the acetate because I wasn't 100% sure, and it ends up being a full page-long calculation. But let me see what I did here. And at the end, I made a comment. I said, even though the excess of base in the form of NaOH is small, it has a much greater effect on pH than the acetate anion. The amount of OH minus contributed by the small amount of excess NaOH is 5 orders of magnitude greater than the amount contributed by the acetate ion. On the next question, the contribution of OH minus made by acetate will be ignored since it is even more insignificant. Yeah. So, as it turns out, I did this big page-long calculation for nothing because it wasn't necessary, because as soon as you get into an excess of strong base, it basically dominates the calculation. So rather than put you through all that, I'm just going to calculate the excess, the OH minus concentration as caused by the excess base. Because it actually comes down to this. Look, at the end of the calculation, I tried including the effect of the acetate anion, and it had essentially no effect. You see, the two contributions are here. One is on the power of -3, and the other one is to the power of -8. So this one here has almost no effect on the pH. This is what's dominating the pH, and that's the effect of the hydroxide. So we're not going to bother doing this calculation, just a waste of time. Let's just only calculate the extra hydroxide ion concentration. Start by erasing. Can't tell you how much easier it is to erase this board. On the other one I was out of breath when I was finished erasing. This one is just, it's a dream. It's better than the ones I had at school. That bump there. Okay. So on 1741E, the hydroxide ion concentration is equal to 5.325 times 10 to the -3 minus 5.25 times 10 to the -3. I use the N is equal to MV. I don't feel like doing that again for you. You can figure that one out. It's pretty easy. So you get an excess of 7.5 times 10 to the -5 moles of sodium hydroxide. Okay? And that's in a total volume of solution. So the hydroxide ion concentration then is going to be 7.5 times 10 to the -5 over the volume, which was 0.0705. Very tiny excess. Liters of solution. Remember, this is the sum of the two solutions, the 35 and the 35.5. What you get is 1.063829787 times 10 to the -3 molar, okay, of NaOH. So that means that your POH is going to be the negative log of this number. 1.06 blah 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 times 10 to the -3. What you get is let's just do it again because I'll get a very slightly different number there. So log of 1.063.829. Well, let's just do it. 7.5 exponent -5 divided 0.0705. 1/940th. Okay, and the log of that is a POH of 2.973 127. So the pH is going to be equal to 14 minus the pOH, and that gives you 11.0268 according to my calculator. So that rounds off to 11.03. So I literally got the same answer as when I did the whole calculation with including the acetate anion concentration. The last part is a greater excess of base. So 1741F, an even greater excess of base. So now you get 2.25 times 10 to the negative 3 over 0.0850 liters. And what you get is an OH minus concentration equal to 2.647 times 10 to the negative 2, which gives you a pH of 12.42 after you do the calculation. Take the negative log of that, get the pOH, add 14 to that, or subtract it from 14, you get 12.42. Okay, so that's wrapping up the homework for tonight. You know what? If I were a betting man, I would say you guys didn't fully get this. So I'd like you to try it tonight, okay? Try 1742, okay? Do that tonight. Tomorrow we'll review it, all right? Get good at it, because soon I'm going to give you a mock test. All right, guys, hang in there. There's another month of school left, pretty much. Your grade is based on what you're going to do in the next month. Impress me, okay? I can't give you an exam. You've got to impress me in the next month. Don't be lying on your bed all day doing nothing. You got no excuse. You're going to university next year. Get on it. See you tomorrow.